All right, ladies and gentlemen, today's class recording has started. So let's, as a review, sort of jump right in here. I'm going to show you an orbital, and I want to see if, with the person next to you, you can come up with the set of orbital numbers that represents that orbital. Okay? So here we go. All right? We're going to start off. Here, right? So that's my nucleus, right? So progression-wise, here's what I want you to do. I'm just going to put the orbitals up. It has all of our notes that we've taken for the past couple days on there, so hopefully you have those in your notes as well. Okay? So right here's first orbital, right? Okay. All right. So here's what I want you to do. Write me the first three quantum numbers, N, L, and M, for that orbital that just went up on the board, that green oval. All right?
Should we draw it?
Probably a good idea, or you can just kind of say this one right here might be a good. You just use sort of an outline, like a big circle, and filling in the space might not necessarily be necessary. But this green oval, what are the first three quantum numbers to represent this orbital? All right. Talk to the person next to you. See if you guys can work it out and come up with the first three quantum numbers, which, like we said, are represented by the letters N, L, and M for this orbital. Discuss with each other. Go.
That's right. Oh, it's zero.
Shape.
Yeah, because it's not an axis. Is that N? It's zero. Is M the axis?
Yeah.
Side.
X the shape.
How about x's?
Axis.
Wait, so with the circle, it can't be like anything else easier?
Jack, the hair's growing.
Oh.
Jack, the hair's growing a lot. It's actually growing like.
No. But it feels different.
I think she's going darker.
So what? So what? No.
What? She gave a million reasons. I didn't think that was very good. It went from like being hyped to one song to the other.
I like how she caught the football when she jumped off the stage. She jumped off the stage.
Chris, who did you want? Who did you want?
I want the Falcons just because the Patriots win too much.
No.
No, the Browns are the best.
That's true.
All right.
I like the one. I like the best.
So there are the first three orbital numbers to represent that orbital.
Whoa.
Okay. How do we do?
Perfect.
Okay. So first, N went up to 4, right? We said that N represents which of our quantum numbers, or what does N
The
represent?
level.
The energy level, and what do we call N as far as the quantum number is concerned? We call it
Principal
the
quantum number.
principal quantum number, right?
Oh my.
And so by changing colors, we went up in energy level, so right, that's why our N went from 3 to 4, okay? Then, what shape is it? Spherical, right? And we said that spherical orbits are what kind of orbital, or what kind of orbitals? S orbitals, right? So S orbitals always get an L value of 0, right? L being the angular momentum quantum number, okay? And then we said that if L is 0, M automatically has to be 0 because M, we said, distinguishes between the different types of orbitals, but there's only one kind of S orbital, right? There aren't multiple S orbitals in this energy level. So if L is 0, M is 0. Timmy, go ahead. Well, technically yes, but when we talk about quantum numbers, we're using them to distinguish this orbital from all the other orbitals. So just to be complete with it, so that the orbital numbers are a modeling system, right? It just, it's a way to tell things apart, blah, 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 blah. So we want that model to be the same for all the orbitals, right? So that we do, but basically it's built in just to have that 0 and 0. It's kind of like, if your house was the only house on a street, like technically you don't necessarily need a house number for that house if it's the only house on the street, but to make it consistent with all the other addresses in Westlake, we would give it a house number. You know what I'm saying? So it's kind of like that. If we're going back to that address analogy, just to keep it consistent with the way we describe all the other orbitals, we should put it in there. Okay?
So L is in between -1 and 1.
L is between,
Or, I mean-
sorry, M, right?
Yeah.
M is between -L and L. Okay? So in this case, for an s orbital, L is equal to 0. Alright?
Yeah.
And that means that if you go from -0 to +0, that's just 0, right, Frank? That's only one possibility. Now, here, right, for p orbitals, L is 1, and that's why M can run from -L through 0, then to +L. Does that make sense?
Yeah.
And then we talked about, right at the end of class on Friday, when we step up to this d orbital, right? D orbitals are assigned an L value of 2. So now, if we go from -L to +L, -2, -1, 0, 1, and 2, right? So L or M runs from -L to +L, right? Does that make sense? All right, how are we feeling? We okay with that? All that stuff kind of come back to us a little bit? Okay. All right, to finish up your outline, oh, not that one. To finish up your outline, let's go to the very last page.
The spin.
And talk about the spin quantum number. So, we use the S value, or the S letter, to represent the spin quantum number. The spin quantum number is important because, we kind of mentioned this on Friday before we left, but just to review or refresh our memory, right? When we talk about an orbital is a place where we are likely to find electrons. And we said that those spaces show up because electrons are trying to do two things. They're trying to get as close as they can to the nucleus, but still stay far away from other electrons, right? So, if too many electrons start ending up in the same spot, now we have a problem. So each orbital can only hold 2 electrons. And that means, and we refer to that idea as the Pauli exclusion principle, and we'll talk about that in just a little bit later on today. So, that means that we have to have a way to distinguish the 2 electrons that are in the same orbital. And we say that those electrons have a different quote-unquote spin. That doesn't necessarily mean that they are actually spinning on their axis like the Earth rotating or something like that. It's not what it means. It's a quality about those electrons that's beyond the scope of what we're going to talk about here, okay? For your guys' purposes, what we have to talk about is the idea that we need to distinguish the 2 electrons that are in that orbital from each other. And therefore, we only need 2 values, +1/2 and -1/2, okay? So, to take this to our drawing, let's go way, way back to the very beginning. All right, we talked about this orbital, okay? So, this is the first energy level. That makes its n value equal to 1. It's an s orbital, so its L value is 0. We know now, even though we didn't know it at the time, we know now that if the L value is 0, the m value has to be what?
0.
Has to be 0 as well. Okay. But within this spherical region surrounding the nucleus, we actually can have, come on, there we go. We can actually have 2 separate electrons. Each of those dots representing a single electron. Now, for this electron over here, it's still in the first energy level. It's still in the s orbital, and because there's only one s orbital, we get that. So this is where the s value comes in, to distinguish these two electrons from each other. S, S. Only two electrons can fit in that space, so one of them has to be plus 1/2, one of them has to be minus 1/2. Does it matter which one's which?
Nope.
Nope, doesn't, right? As long as we can tell them apart from each other, as long as they're different from each other. So I'm going to call this one plus 1/2, and I'm going to call this one minus 1/2. Okay?
So quantum numbers tell the orbitals apart or the electrons apart?
Technically, they're going to tell the orbitals until we start filling up those orbitals. Then they're going to be telling electrons apart, right? I know, for the most part, I've been describing the orbitals, and that's true. And that's good until we get to the fact that each orbital can actually have two electrons in it, so now we have to distinguish them, all right? So yeah, Jack, I was actually thinking about that this morning. I'm like, I hope that doesn't get confusing, and, you know, I hope that it's that's good. Okay. Sammy, good. It doesn't. We could have called it +1 and -1 if we wanted to, or whatever. Like Sammy, this is just an arbitrary way of defining or separating them from each other. Okay. It doesn't necessarily the 1/2 doesn't actually represent anything. It's just a way of telling those two electrons apart from one another. So don't try to read into that too much. Like, yeah, it's not like that 1/2 is representing something. It's just a way of telling them apart from each other. Is that a good enough answer for now? All right. So here we are. We have completed this huge drawing right here, right? We talked about a bunch of different orbitals, and there are even more orbitals than we've talked about up here, right? There's more spaces, ones that are even harder to draw, or even farther out from the nucleus, right? Higher energy levels as we go out, right? So we'd have to add a new color, et cetera, okay? But this is confusing and really hard to draw to represent if we had to do multiple electrons, right? If we take a look at an atom that has 10 electrons or 15 electrons, trying to put them in this drawing is going to be confusing. And so we need to do something besides this to simplify this idea to hopefully represent these electrons a little bit better, okay? So we are going to, in order to do that, we are going to take a look at our next section, which is about orbital filling and orbital diagrams, okay? Oh, sorry, beginning of class, I forgot something up on the board. You are going to need a periodic table. The only thing on the periodic table you need today is atomic number. So if you have something on your phone where you can read the atomic number, that's great. If you want to grab a book, you can do that. If you can read the board, you can read the side, that's fine too, okay? So we need to know atomic number today to figure this out, all right? Does anybody want to go grab the periodic table, or are we just gonna roll?
Oh, yeah.
That's not an answer. So, that wasn't an answer to my question. So, are we going with no on grabbing periodic tables? Is that okay?
Yeah.
Okay. You know what? I'll show you periodic table up on the board. How's that? So,
Original
nice. Can you read the numbers on it?
Yeah.
Okay. Fine then. All right. So Jack,
Yes.
the question you just asked is a good. The question you just asked about is a good way to start this discussion. Okay. So we have learned something similar to the off-bow principle before, and we learned it in relation to this baseball. If I let this baseball go, what happens to it? It drops. Why? Gravity is how it happens. Why does it happen? We let it go. Why did we say the baseball prefers to be there than here? Think about it from an energy standpoint, right? It has less energy. Specifically, what kind of energy? Potential. All right? And that's an important part of the off-bow principle. Orbitals are filled from lowest energy to highest energy. And we kind of talked about this a little bit too with that baseball, right? If we started filling this room with baseballs, which part of the room would get filled up first?
The bottom.
The floor would get filled up first, right? Does that make sense? And then once the floor got filled up, then the layer above the floor would get filled up. Why? Because that's the next lowest energy. Same thing holds true for all of those orbitals that we just drew on that picture. Orbitals are filled from lowest energy to highest energy. And we know from studying what Bohr said, even though his model as a whole wasn't correct, some of the aspects of his model were correct. So where are our lowest energy orbitals? Closer to the nucleus. So, right, orbitals closer to the nucleus are the ones that have lower energy, and therefore they are the ones that are going to get filled up first. And to keep track of those orbitals, we are going to use this chart. It's actually two charts. It's the same chart, just looking at it in a different way, representing information in a different way. I prefer this chart on the left. It's the one that I use most often, and it's the one that we're going to use in class most often too. Okay. So if we take a look at this chart on the left, along the y-axis of this chart, it's labeled as increasing energy of electrons in orbitals, right? Over here on the far left. And there's an arrow pointing upwards, meaning, where are we going to start on this chart?
The bottom.
On the bottom, right? Because we want low energy to high energy, all right? And if we start from the bottom, what's the first orbital that we run into?
1s.
1s, right? On our drawing, that was the yellow sphere that we drew first, right? That's why we drew it first, because it's the one closest to the nucleus. But in terms of orbital filling, it's the one that has the lowest energy. So that's the orbital that's going to fill up first. After that one's filled, we just learned what does it take to fill a 1s orbital?
2 electrons.
2 electrons. Once we fill up that 1s orbital with 2 electrons, we move our way up the chart. What's the next orbital that we hit if we move from the bottom upward? 2s, right? And on our picture that we drew before, the next thing that we drew, right, we started with the yellow sphere, and then we filled up, or then we drew the red sphere, right? It's an s orbital because it's a sphere, but it was a different color, and that's why we went from 1 to 2, right? That makes sense? Okay? So, we're going to use this over the next couple days to draw a simplified version of that really complex picture we've been drawing over the past couple days. A simplified version of that really complex picture we've been drawing over the past couple days is called an orbital diagram. Okay? An orbital diagram shows the distribution of electrons within orbitals. Orbital diagrams show the distribution of electrons within our orbitals. We use circles or lines or boxes to represent the different orbitals. There is no one accepted way of doing it, just depending on the book that we look at or the problem set that I give you to work on. Sometimes we'll see circles, sometimes we'll see lines, sometimes we'll see boxes. But then we always use arrows to represent individual electrons. So orbital diagrams look something like this. A circle with arrows inside of it, or a line that has an arrow above it, okay? This is going to be our orbital diagram. Some combination of circles, boxes, lines, and arrows, okay? All right, and this is not an orbital diagram itself. This is more of a representation of what an orbital diagram could look like. So we're going to start drawing real orbital diagrams right now. All right? Ready to go? Yeah. Here we go. All right. So let's start not here, but here. And the first thing that shows up on your outline is hydrogen, down at the very, very bottom of the first page, right? And it says orbital diagram practice hydrogen, okay? So, an orbital diagram shows the distribution of electrons in the orbitals that surround the nucleus of an atom. That being the case, before we can tell you which orbitals are full and which orbitals aren't full, we need to know how many electrons we're talking about. And that's where the periodic table part comes in. What value on the periodic table tells us how many electrons we have to worry about?
Atomic number.
The atomic number. So, we look at hydrogen, and we find out that hydrogen's atomic number is what? 1. And that means that hydrogen has 1 electron that we have to place. Okay? So, you can draw that down. Like, all we're doing mostly for the rest of the time is basically filling in, drawing orbital diagrams. So down at the bottom, underneath hydrogen, right, you might want to make a note that hydrogen has 1 electron, because that's going to be important for us. Okay? And so I just use that notation, right, E with the negative exponent to represent electron. Okay? All right. We just learned that the off-bow principle tells us that orbitals are filled from lowest energy to highest energy. So this chart that shows up on the front page, you're still looking at, along the x-axis, or along the y-axis, right, increasing energy of electrons in orbitals. We said we're going to start at the bottom. And we already said the first orbital that we run into is which orbital?
1s.
1s. Okay? So here's what we're going to do. This is how I draw my orbital diagrams. First, I'm going to draw a line to represent that orbital. But then I have to label that orbital. So underneath the line, I'm going to label it as 1s. Okay? Just like that for starters. Okay? Now, even though I haven't drawn as detailed of a picture as I drew before, if I draw a line and tell you it's an orbital and it's a 1s orbital, you should be able to tell me 2 things about that orbital. Knowing that this is a 1s orbital, what can you tell me about it? Someone besides Jack. If it's a 1s orbital, what's one thing you can tell me about it, Sammy? It's a sphere. You know that because what kind of an orbital is it? S orbital, right? What does the 1 tell us about this orbital? Someone besides Jack. The energy level. If it's a low number, what does that mean? Where is it? Close to the nucleus, right? This is an s orbital that's close to the nucleus, a spherical orbital that's close to the nucleus, all right? But just because it's there doesn't mean there's electrons in it. In this case, though, we only have 1 electron to place. So I'm going to take this orbital and I'm going to draw 1 arrow. A lot of times you'll see that when we draw these orbitals, or draw these electrons, we'll just use one-sided arrows. That's really just to save time, all right? So here, I'm going to draw this like this, all right, to represent 1 electron in the 1s orbital. Orbital diagram number 1. Boom. We didn't have to draw an x-axis, a y-axis, and a z-axis. We didn't have to draw a sphere. We didn't have to draw the n, l, and the m numbers, right? This is representing electrons in the hydrogen atom. Okay? Good for starters? Okay. Let's logically move on to the next one, which I believe is at the top of the second page, and it's helium, yes? Okay. All right, so if we're going to draw an orbital diagram showing the distribution of electrons in orbitals, what do we have to know first?
How many electrons?
How many electrons? Chris, how many electrons does helium have?
2.
2. How do you know that helium has 2 electrons?
The atomic number.
That's helium's atomic number. Good.
Yeah.
Okay? All right, so here's our chart showing the energy of the different orbitals. All right? First orbital we run into is always the 1s orbital. So I'm going to draw a line like this, and I'm going to label it as 1s. Okay? We know that we have to place 2 electrons. Okay? So, I'm going to draw my first electron, and that looks a lot like hydrogen's, but we know that helium has 1 more electron. We learned at the end of the last outline how many electrons can each orbital hold? 2. Okay? Now, we refer to that idea as the Pauli exclusion principle. Let's go here. Okay. Alright, so helium is our first example of the Pauli exclusion principle. Each orbital can only contain 2 electrons, but we need to distinguish them from one another. So, we say that they have opposite spin. When we are talking about the spin quantum number, we called one of them +1/2 and one of them -1/2. But there's no numbers on an orbital diagram, but we still have to show that those electrons are different from one another. And so the way we do that is with the direction of our arrow. We show the different spins on our electrons with one arrow up and one arrow down. Okay? And that is our orbital diagram for helium. Eric, good. Because orbitals are always going to fill up lowest to highest, right? While around the helium nucleus, all of this exists, most of them are empty. Because there's just not electrons to fill them up, right? Just like in a new development, Eric, right? We build a street, we build a bunch of houses. Just because the houses are there doesn't necessarily mean families are living in them yet, right? We have to build up to all the families living in those houses. Does that make sense? These are the houses, electrons are the people that live in those houses. Okay? All right, good so far? Okay, let's go back here. And let's talk about our next element. Next element on the periodic table is lithium. Okay? All right, so if we're going to draw an orbital diagram for lithium showing the distribution of electrons, right, we need to know how many electrons we're talking about. Lithium's atomic number is 3, so that means we have to place 3 electrons. Okay. Using our chart, right, we know that the first orbital that always gets filled is what?
1s.
1s. Here's my line representing the 1s orbital. I label it as 1s. What do we know about that 1s orbital? It can only hold 2 electrons, right? We know that it's spherical. We know that it's close to the nucleus. We also know that it can only hold 2 electrons. So, there. Okay? At the beginning of this outline, we learned about something called the off-bow principle. The off-bow principle says orbitals get filled from low energy to high energy. So we examine our chart. You guys have that chart on the front page, or if you can read mine up on the front, right? So we said we start looking at this chart from the bottom and then we move up. Okay? So the next orbital that we run into as we move up the chart is which orbital? 2s. So now I need to add a second orbital. I do that by drawing another line. That line now represents which orbital?
2s.
The 2s orbital. Okay? The fact that it's labeled as 2s should tell you 2 things about it. When that line is representing a 2s orbital, what 2 things can you tell me about the 2s orbital? It has higher energy. We went from 1 to 2. What else can you tell me about it? Well, hold on to that just for a second. What can you tell me about the orbital itself? It's what shape? Spherical. Okay? That's the S part. So it's higher energy because we went from 1 to 2, but it's still spherical. This is the red circle that it was on my drawing. Right? Eric, how many electrons do we still have to place though? One. All right. So we're gonna put that one electron in there just like this. Okay.
How many is lithium? Oh, wait, no,
Didn't you
boron.
just tell me?
Boron.
All right. Hold on a second. Before we do that, let's say I did this. Is that an acceptable orbital diagram for lithium?
Yes.
Yeah.
Yeah.
The directions are telling us what? The direction of the arrow is used for what?
Just to distinguish electron from one.
Telling one electron from the other. If there's only one electron in in that box, does it matter whether we go up or down first? It really doesn't, right? It's only important that when we get a second arrow, it has to be the other direction from what we originally drew. Okay? The arrow direction is only there to distinguish one electron from the other electron. If there is no other electron, it doesn't matter which way we draw that arrow. Okay? Just by convention, I will usually go up first and down second, but it really doesn't matter. Okay? Chris, what's the next element we're talking about?
Boron.
Boron, all right? Did you look on Jack's periodic table and find out about boron?
Yeah, it's
All right.
the carbon star.
Boron has 5 electrons. All right. So, Aufbau principle tells us lowest energy to highest energy. We know the lowest energy orbital is always what?
1s.
1s.
1s. Line. 1s. How many electrons can that 1s orbital hold? 2. 1, 2. Okay. All right. That one's full. We move up the chart. Next orbital we run into is 2s. Here's my line. Here's 2s. How many electrons can the 2s orbital hold? 2. Right? Here, here. All right? We're still not done yet, though. We have to place how many electrons? One more, right? 5 total. All right, so we go up the chart. What's the next thing that we run into? 2p. It's not in the same column, right? But it is the next closest to the bottom, even though it's one column over. Yes? Okay? That's the next lowest energy orbital. But on the chart, how many lines are there next to 2p? There are 3 of them. Because what do we know about p orbitals? How many p orbitals are there?
3.
There are 3 of them. Do we remember those pictures, right? Chris, what do we know about p orbitals? What shape are they? They're figure 8 shape. And we talked about, right, there are 3 of them. One on the horizontal axis, one on the vertical axis, one on the front back axis. Okay? What do we see about these 3 lines? Where are they in relation to the bottom of the chart? How high up are they on the chart?
They're all even.
They are even. What is that telling you about those 3 orbitals? Same energy. Okay? That being said, when we run into a situation where we have multiple orbitals that are the same energy, we draw all 3 of them.
Oh my god.
Okay?
Just leave them empty.
Not yet. Because, right, for boron, how many electrons do we have? 5. So we still have another electron to go. Okay? Where does it go? Probably doesn't matter. She's right. Doesn't matter. Because orbitals fill from lowest to highest. All 3 of these are exactly the same energy. Does it matter where they go? Doesn't. Okay? Generally speaking, we're going to fill up this one first. Okay? But that's just usually by convention. Okay? Good there. All right. let's hold it there for now. We'll finish this up tomorrow, and then we'll talk about electron configurations on Wednesday.
Periodic table organized by the highest octave.
There's a reason why it's that